Oh, the message has changed on Zoom. It now says the content of this meeting is being sent to a third party. It used to say you are now streaming or something like that.
Oh, to me it
I'm still
says this
getting
meeting
straight.
is being live streamed.
Yeah.
Yeah, I just, my Zoom updated itself just now before.
Oh,
So
I should do
The
that.
update.
it's being sent to a third party is the new legal term for streaming. It's like streaming was not legal enough, legalese enough.
Okay. All right. So yeah, last time we like really got stuck into some type equality. We had this well, I should share my screen just to give some context. Yeah, all right. So okay. So we corrected the definition of this equality for types. So instead of this returning a prop, and I think this is a sort in the equal, but or it's yeah, or it's a type. It's probably a sort. No.
It says sort U+1.
Okay. Which is
a type U.
yeah. But yeah, the main point is it returns a prop and not a type. And prop is kind of a sort in universe 0, and type is a sort in universe 1 and up. And our thinking is that if we have a type, then we have proof relevance. And if we have prop, then we have proof irrelevance, where prop basically means when you compile, just delete. I don't care. I'm not going to compile this code. It's good for proofs at compile time, but I'm not going to generate any code with it. Let me put it that way. And then for types, we're thinking like the proof is relevant. And this is kind of like code where we actually care that proofs are different. And specifically for our case on regular expressions, we care because it represents different parses of the string. Okay, that's the background. And so we got stuck with really things like this, like just proving not. So here's it on normal equality as code, but you could also just, I think this is just by contradiction, probably. No, I don't get lucky. Okay. Okay.
Yeah, it's not quite as good as
but there we go.
As rock.
Yeah, it's pretty simple, right? But writing it out as code is, especially with the type equality, is quite a lot of work. Although this is kind of the same in this case. But oh yeah, and these we actually couldn't figure this out last time, so I actually want to credit Petro for commenting on the YouTube video and telling us how to do it. I think our versions are somewhere here. We're trying to use no confusion, which was pretty tough.
Confusing.
Yeah, and in
well, we
Agda,
didn't figure these out, by the way. This was just copy and paste them from the output.
Yeah, we took this tactic and we just printed it out with like this. And that's how we did this. But yeah, Petro showed us like there's a much simpler way that we could do this. It's still pretty annoying to write a motive, in my opinion. and in Agda, this is very, very simple, where it's all just kind of inferred by the type checker because of how it does elimination. And so here's Petro's comment. I don't know if we can read this, but this is just him providing the code which I copied, and it works perfectly, which is also pretty impressive to copy from YouTube, and all the code just works, but with all these Unicode things, but yeah, that's good. But this comment is really interesting. So he says, like, in Agda, these proofs are simpler because it uses the K rule instead of J rule as the elimination rule for identity types. So you can turn this off in Agda, as far as I know. But all others that I know of, Coq, Lean, Idris, and Agda, using this without K option, uses the J rule, which requires large elimination, not just functions with no cases. And it seems like there is a lean way of doing things using no confusion. So that's the code we had here, which hopefully there's a simpler way to use no confusion that we don't know. And yeah, because this no confusion is a auto-generated function on net. So that's why I couldn't figure out a way to write our own for type, because there's no confusion operates on prop. I think I can show that. Can I? Okay, that's fine. And then, am I lucky enough?
I think you get this no confusion for every inductive type that you define.
Yeah. So yeah, here's the generated function. I think. Yeah.
Yeah.
So this is generated. Oh, it is on sort. So this should work on type and prop. Just yeah, okay. So okay, so that's interesting. Something to come back to. Yeah, so that's the comment he made. So that was interesting for me, is that, like, yeah, Agda has a different way of doing elimination using the K rule instead of the J rule. Maybe it would be interesting to know when you would want to use without K and when you would want to use with K.
So interestingly, in Conol's repo, at least some of the files have without K option, the without K option in a pragma.
Does
I don't know if that is all of them.
Does the calculus.agda have one? Because that's kind of the one where we.
So calculus doesn't have it.
Okay.
So it's using, I imagine that means it's using K, but for example, predicate uses without K.
Okay.
Okay, indeed.
Yeah. I walked into the trap.
We got punning is the name of the game on this show.
Yeah. You got me there. So in this,
yes. So if you go to like
calculus
predicate.agda, or yeah, this one doesn't have without K.
Yeah, but then you're saying,
then if you go
predicate
as without K.
As without K. So that's interesting. So you can mix and match them. So that means it doesn't matter which elimination you use, the proofs are still sound, right? Like they're interchangeable.
Unless it's viral, unless if you import without K, then
predicate
you
seems
have
pretty
without K.
close. High. It's high.
Mhm.
Mm. So no, it's pretty low. Where calculus, I think, would import predicate. No. Okay, well, Jan, have you ever played around with without K? Without?
Oh, no, I haven't. I mean, I've seen it sometimes, mostly in cubical Agda, but
Mm.
I haven't really played with it that much.
So you would say it's more popular not to turn it on. So
I would say, I mean,
with K.
I think that initially Agda always had it, and then that prevented extending the type theory in a certain direction. So they added it as an option, and then people try to use without K whenever possible. So the proofs that they write are also usable in projects that do not use the axiom K.
Mm.
That's my perception, but I'm not. Yeah,
Oh,
I'm
so
not an expert on this.
does K introduce an axiom?
Yeah. So as far as I know, and I could be wrong here, we should double check.
Hmm?
I mean, the axiom K is that any two proofs of the same type are the same. So basically, proof irrelevance, right?
Oh. Oh, that's interesting. Wow. Okay. So are you saying when you say without K,
Mhm.
then it's proof irrelevant?
It's proof relevant.
Relevant.
Yeah. But that's my intuition. I'm not. He shouldn't take my word for it.
Mm.
Uh,
That's very interesting. So that, okay, so it's kind of like it turns type into prop. If like your axiom on the K axiom is correct, then I'm gonna say it turns type into prop. As like almost saying like take us one universe down.
yeah, I'm not sure. So when you're using K, you can pattern match on graphle, and you can unify. Well, when you pattern match, it automatically unifies the variables. But when you don't have K, then you cannot pattern match on graphle. And equality proofs get more involved. That's the practical effect that I noticed.
That's very interesting. Wow. All right. Do you have anything else to add? Otherwise, we're gonna make it even more complicated.
Should we maybe Google the definition of axiom K to make sure we didn't mess that up?
Yeah, so there's the docs for without K, which have some code examples.
Okay. For inactive?
Do you want to share your
Yes.
screen?
Yeah.
Cool. Yeah, it's just hard to Google things while you are sharing a screen. It's
Yeah, exactly.
very awkward. So it's always great to have someone who's not sharing Google and then switch.
So I initially went to NLab, which of course is no use to me.
Oh wow.
This is K.
Oh great.
So-
Well, okay, wait. Well, you can read pi.
You can read pi.
Yeah, so for all types A, there
Yes.
for all x, so these are just parameters. And then
Yes.
I don't know what that means.
So this is
Equality.
the equalities or proofs of X, I guess. X equals X.
Or identity.
Ah, right.
Yeah. The identity type of equivalences of term X, of the term X. So these are all the different proofs of X equals X. There's more than one of them.
Okay. And then we say also the because like we're getting another parameter here, the reflexivity of A.
Mm.
I think IDA is just the identity type.
Yeah, identity type of equivalences.
Oh,
So I think it is literally this is the proofs of X equals X.
okay. So if we have that, then we can get
So
P.
maybe we could even prove this in Agda. So
Oh.
this formula for the axiom K, I think we could prove that.
Okay. I think this might be here.
Ah, okay.
Yes,
exactly. Yeah.
So this is the
Oh, this is much
implementation.
more readable. Yes. Okay, cool.
I mean, okay, so this is the type of.
Okay, I see. I see. Yeah, and riffle is that. Then we get.
I mean, raffle, and then an inhabitant of X equals X.
Hmm. So there's the pattern matching on riffle is happening on line 3 of that. Is that
Right?
Yeah. This is
Yes.
matching.
Yes.
okay?
Pattern matching with the constructor raffle on the argument X equals X causes X be unified with X, which fails because you want to do. Yeah, there's many of these, not just one. Many raffles.
Okay. Okay. And then this is the J rule.
The J rule is okay. The J rule is saying what? So we now have two. We have X and Y. So now our equality is parameterized by X and Y.
X and Y.
Not just X. Not just X.
Mm.
What does this mean here? X, Y, A, and then
Yeah, it feels
is
like
this like a for all or something?
it
I don't know.
must be. Must be. Yeah, yeah.
Okay, so this is like a pi.
Yeah, I understand.
And so we've got they've got P, little p, which is this, I guess.
X and
And
dot X.
Dot
The
X.
dot
What
X
is dot
is
X?
Y at this point, but why is it dot X?
What does the dot mean?
So dot X.
Oh, it's just bind?
It's a they call it irrefutable pattern. You know,
Irrefutable pattern.
yeah.
Sounds serious.
Don't ask me the definition of it, but it's probably in the documentation.
Okay, pattern matching with the constructor referral on the argument x equals y causes x be unified with y.
Well, you're gonna. It looks like you're manually unifying them, right? Like you're going, I'm going to pattern match JP XX. So now I've told the program that Y is X. Where at the top it kind of, at the K rule it kind of happens automatically, or more, or it's, yeah.
If I just paste this into Agda and get rid of the dot, see what the error message says.
It's gonna complain that you have two patterns with the same name. on two
Oh, well,
variables.
maybe give it a different name. I don't know. Oh, but we want it to be the same. Does that do it?
Yeah, we want it to be the same.
Does that
So maybe
mean error?
So the
Doesn't
dot
look like it's
not in code, is it?
Oh,
Oh.
yeah.
Or it is.
I thought it would be here. Oh, if I put it in
Yeah,
code,
it has to
maybe.
be inside code.
But what about this stuff?
Oh, you have
It is-
endcon at line 20.
Oh, right. Thank you.
Yeah, there we go.
Oh, it doesn't have no idea what we're talking about. That's
Hmm.
fine. It has no idea what we're talking about.
Well,
I need to import some stuff.
yeah.
I don't know. Maybe it will help me. No. Doesn't understand. This is all the Agda I have on my machine, so examples. Probably not. Oh, it does. There we go.
That's good.
Now what do I want to do with this?
So if you put a y, so dot y,
Yeah.
what does happen?
Also, it doesn't complain.
No. So maybe the dot x is to emphasize that at that point the checker already knows that x and y match.
Because that's what the REFL is doing, is it? It's mean. So if I do the I don't remember the syntax. What's the whole?
Question mark.
Question mark. Okay. So if I do Agda do something. Agda refine. Yeah. No, it doesn't understand.
So you want Agda to give you the reference?
Yeah, I just wanted it to figure out this
So you can start
before.
with P. So
Yeah,
right.
with P and then put a thing here.
Right. So you
Then-
can also do that by creating the hole first, and then
Uh-huh.
manually writing P inside of the hole, and then calling refine.
Okay, how do I get rid of the hole now?
It's tricky to write the P inside.
Yeah.
Okay, so now you load the.
Yeah,
No.
I know there's bindings. I just don't remember any of them. Next, goal. Yes.
But now you have the P outside.
Yeah. So now I can refine this one. Oh no.
No. So what I meant is, so if you delete the P.
Yeah.
And you load the file, and then you type P inside of the hole.
Yeah.
And then you try to refine the hole. It will move the P outside, yeah, because it refines
Yeah.
it. Okay. And
I was hoping it was going to figure out that x is equal to y and.
Well, you can try. Let's try Agda auto. Maybe it does
Ugh.
something.
Auto.
This one.
Yeah. Okay. So maybe you were saying this is just a way of labeling something, like a duplicate label, but when you want it to be a duplicate, but
Yeah, or
not
not
complain.
not even a duplicate, but well, let's say that the .x was, I don't know, a list, and from the previous patterns you knew you could discard nil. Maybe, well, yeah, I was thinking maybe you could use the dot. No. Yeah, I'm not sure. No. I think this could be mostly for names. To say that these two variables unify in the pattern.
So in the files that have without k, then this magic is using this axiom instead of k in order to figure stuff out.
Yeah.
And this was good enough in the calculus module. A helpful comment in YouTube was saying that this is not available in COP or
No.
Lean.
This is available.
Only this is available. Okay.
You don't get the K option.
Yeah.
Only Agda has the K option, and it is Agda's default. It
Okay.
is kind of interesting.
So what is, do we know like what's so limiting about K? Like
I think it tries to explain.
okay.
So the K option seems much better at figuring out contradiction, like in a practical sense. But because like Lean uses the J rule, we have to write a lot more to get us there. Like the contradiction tactic still works well, but if you just want to write code and not use tactics, then K seems to be better.
Termination checking universe levels. Okay, so it must be to do with pattern matching then. With K, then we just have more.
So here it says that you should use this for theories that do not support the uniqueness of identity proofs, right?
Oh, is that that what UIP is? Okay.
Are we really in a situation where we don't have uniqueness of identity proofs?
Yes.
Okay.
They also mentioned this in the Zulub thread UIP a lot, and I was like, what is this?
Yeah.
Please explain.
I mean, for the regex stuff, do we not have uniqueness of identity proofs in the for the regex stuff?
Maybe can we take one step back for me?
Yeah.
What is uniqueness of identity, right?
So identity is this here.
Yeah.
X equals X, and so there's only with K, there's only one inhabitant of this, which is Refl.
Okay.
So like in this one, you can pattern match on Refl.
Mm-hmm. And there's only one. So
yeah, I think that's what this means.
So this is, well, like if you think of the inductive principle for any singleton type, it looks pretty much like this. For instance, the inductive principle of the unit type
yeah.
would be if you give me P of, well, the unit constructor.
Yeah.
And any type of the unit, any term of the unit type, then I'll prove that that term satisfies the predicate. Right. It's very similar.
Yeah.
Oh. I think I'm still struggling. So like, I think I can. One thing I think I can understand maybe is like we can only pattern match on things that we know how they were constructed, right? So if that thing has only one constructor, then it has to be like uniquely constructed. So if it's Refl, it has only one constructor. So there's only one way that X equals X could have been constructed.
Exactly.
And
then in homotopy type theory, this is not true.
And that's why you cannot pattern match on Refl, because you don't know how it was constructed.
Yes.
It's not unique.
Yeah. You can't pattern match on a value of the. So you could pattern match on like Y or something here, but not on a. You can, if you pattern match, you can pattern match on a Refl, but then you'd need another pattern as well, another clause for the other things.
Well, only if you knew what they were.
Well, you could have a wildcard. I mean, a wildcard pattern.
Yeah. Okay, that is.
But are we really in that situation though?
Okay.
It's
now explain your question. Now that I understand the premise.
Yeah. So my question is like, when we're doing our like regular expression stuff, are we really in the situation where we don't have uniqueness of identity proofs? So where we have more than one inhabitant of this type, X equals X. Is this really necessary?
So when you're using prop, aren't you like implicitly accepting that you have uniqueness of proofs?
No, I think when you're in prop, you're accepting that you don't have uniqueness of proofs, and you don't care.
But if you cannot,
You only care that the
I
proof
see.
exists. You don't care what it is, and you will never pattern match. You cannot. So
But if
it's
I look at like,
like two
if I look at the
things. Like yeah, in props like I've lost. Like yeah, you will never pattern match on it, right?
right.
Because it's not unique, but you also don't care that it's not unique. That's the other part.
Right. Yeah.
Where with K option, like I know it's not. Oh, I like.
yeah, I could sort of see what you're saying, but in
I'm struggling.
there's no like in like in Coq, we always have to worry about whether you're in prop or not. There's like this distinction in everything, and Agda gets around this by having this axiom K, saying that you can pattern match on it. Where in Coq there are certain things you can't do because they're not computationally relevant.
And that's maybe
that was a curious thing that in Agda you never have to worry about that, but maybe that's because of axiom K.
And that might also be why it's so easy to construct contradiction, because you could pattern match so deeply. Or at some point.
There's one thing I don't understand. Like if I look at Eek, it only has one constructor.
Yeah.
In Lean. So all this stuff about, well, I don't know how many things, how many inhabitants, A equals A has, X equals X has. Well, we know it's here. That seems clear enough that there's only one constructor.
But you cannot look into that because it is prop, right? So it's invisible to the type system.
Ah, okay. Right. That's that. I think that answers that part. But in RTEQ, we definitely we still have one constructor, right? We don't have more than one proof of equality.
So what's
interesting? Is that wrong?
What's interesting is maybe it works, but I was not able to pattern match on TEQ. Like it probably works, but I couldn't figure it out. But if you look below on line 36, and then 36 and 43, you can see I have found a way, well, by copy and pasting and modifying. So I didn't figure this out, but I found a way, literally found, to go from TEQ to EQ and back.
No, I think you can claim that you found it. You were computer assisted discovery of this function.
No. I actually I searched and I found it, but like I didn't write it. So I found a way makes it sound like I wrote it.
Yeah.
Searching through the.
Well, I think I'm still impressed. Is what I'm saying. I'm still impressed.
So. Yeah, I am also impressed. But yeah, but it's interesting because what we have at the top is something that goes from type to prop on 36, and on 43 we have something that goes from prop to type, which is usually not from prop to type, which is usually not illegal, which is usually illegal. Because
haven't we passed some kind of impermeable barrier at that point?
Yeah, you can't like pattern match on prop, right? So like again, but somehow here,
is this a bug?
Well, no, apparently no.
Okay. This gives us like a portal in which we can like transfer garbage into the into the world, right?
Yeah, so this makes it's really hard because now we can just go back and forth between proof relevance and irrelevance. So if you scroll down a
But
bit,
one thing that you will not be able to do
Mhm.
is if you go from EQ to TEQ
Yeah,
and then go back, you'll not be able to prove that you went back to the original proof.
Ah, maybe that's the key then. Yes.
well, okay, I counter that with, if you scroll down,
Oh no!
Oh no! Immediately proved wrong.
on line 61, like 61,
Mhm.
I have a proof for conger arg in EQ. So I go, but I need it to be in TEQ. So I go from EQ to TEQ, from TEQ to EQ, pass that to the proof, and then I take that proof that's in EQ and I turn it back into TEQ. On line 62.
Yeah. But the statement on line 61 is not what I was saying. I
Okay.
believe.
Okay, good.
Right, so this is congruence. So this is fine.
Okay, what were you saying?
So what I was saying is, so you have, can you help write it down, Paul?
Yeah.
Okay,
So something like this, but with the gubbins at the beginning.
right. Yeah. Right.
We don't have an F, or do we have
No,
an
we
F?
don't have
We
we
an
don't have an F.
Yes.
So we
We'll have an
have
EQ.
we have a proof in EQ,
Mhm.
Yeah.
right? So my claim is that we we cannot prove that H is equal to back and forth from TEQ and back to EQ using the functions that Walter defined above.
So we can't prove that H is equal to
I don't remember
this
the name
thing,
of those functions.
TEQ of EQ.
Oh yeah, exactly, yeah.
This which way around though?
I think this is the inner one, and then the outer one is the other one.
This one. Okay.
Yeah.
Give it a try.
Yeah, you can't do that.
Yeah, so that was
but
I
only
meant.
because you can't prove that a prop is equal to another prop. But
Okay.
Oh,
but maybe you could do the reverse.
Well, but you cannot well right. But you could prove that if you have an EQ, I mean, in the REFL case, you can still prove that, right? So what I mean is, you can still prove H equals H here.
I like maybe like we could
Can we-
prove that if
Can we try that?
if H is TEQ,
No,
then
no. Like H being EQ, can we still prove that H is equal to H?
no, because no, because like because you can't prove that props are equal to each other. You can't say EQ 1 equals 1, 1 equals 1. Like you can't prove.
so you can't do something like well,
Yeah.
no,
Yeah, you can't prove that.
Interesting.
Right. In this case, sure. But what about with H?
But
So H
is an EQ.
is of type EQ.
So that
Yeah, but
equal sign,
it has a name.
that
Can we try to copy this Jan's counterexample and then we
Yeah.
remove the EQ of TQ and TQ of EQ?
Yes. Do you want to prove H equal HH?
Yeah. I believe this should be possible. I could be wrong.
No, so this is what I'm saying is not possible.
Okay, let's find out.
That's oh,
Because what you'll
What
have
should
to
I
do is do pattern matching on EQ, which
No, but you should be able to use REFL or something.
okay,
Like pattern
Yeah,
matching is not needed here.
that's worth a
Okay.
shot. That
what am I
sounds.
doing wrong already? I don't remember
I
anything.
don't think there's
So
anything to
can't I
intro.
do that?
There's nothing to intro.
Oh, what's on this?
It's all intro.
Oh,
Because,
sorry, it's all introed already. Yes.
Yeah.
So I should be raffle.
Or I
Oh.
think without the E.
Or
Yeah.
it definitely is a constructor. So
Ah.
uh
What?
yeah, okay. We've learned something.
Okay.
But it's gonna make Walter's brain explode now. He's just gonna quit the stream.
What the fuck?
We'll go offline in a second, guys.
Oh. What? Like, what?
Hmm.
So yeah, maybe so. The point is you can't you
Huh?
we don't have to pattern match here.
Yeah.
We
Exactly.
have the constructor on the nose. We just have a constructor.
Okay, because they have the same name.
Yeah.
Okay, wow, okay. But still, I would have disallowed this just for consistency.
if Walter's designing the logical universe, it's not allowed.
Yeah, no.
We should have like we should have like a flag, a new flag with Walter's exceptions.
It's with W.
Yeah. It's or it's like if you want W, you need to put this flag on. Yeah.
Yeah. What the hell? Okay, this is okay. With the bottom one, we won't be able to prove, right? Just
No.
I mean, please try.
What do you want me to do? Revel?
Yeah. Oh my god.
Oh
no.
crap! I might.
No.
No.
No. Okay, now I quit.
Right. I'll hold on a second. Let me just lake build this.
Yeah. Just. Oh no. Did you save?
What?
No, you
Yeah.
didn't.
What is going on here?
Please save. Okay. Go again.
Oh no! Here we are. Look. Oh. What is
No,
this?
no. That's a different proof.
Yeah.
Okay. Good.
Yeah, that's correct.
Compiler says yes.
Well.
I don't even know.
So
I mean, this
why?
you're claiming this function could be a bug or something.
No, I'm not claiming anything anymore.
Let's not claim
We're done with
anymore.
claims today. Okay.
I mean, someone could have won a lot of money off me now because I was like so sure about these things. Wow.
Well, that's an interesting property, right?
Yes. Yeah, it is actually keep those proofs. They're very good proofs to have.
I'm not. Listen, they are not countries.
But why?
We should print them and see what's going on. I mean, okay, so I don't need to use a tactic, do I?
Oh, right.
So I can just say referl something.
Yeah, I think you just need to say eq.referl, sorry. And then H.
Something.
Yes.
H.
Okay.
But then,
This one may or may not do it. Yeah, there we go.
So, okay, I have a hypothesis. Let's see if it makes sense for you. It happens that these two functions that Walter defined are actually inverses.
yeah,
But if these functions were not something concrete, but let's say some parameter, then of course this wouldn't be provable with REFL.
yeah.
Right.
Jan's example 3, and then just do a by. I just want to see the proof state.
Oops. Yes. Bye.
Sorry, no, I meant so.
Yeah. I just want to. I just.
Oh, but
Okay.
Walter
Yeah,
just
yeah.
wanted to see the.
Yeah,
see.
I'm not doing something right here. Unexpected. I can't do that. What? That's right, isn't it?
You just tab. Just tab.
Oh, sorry.
That's it.
I'm getting a parser error.
Yeah, that's fine.
Okay.
Yeah.
Oh, it's
Because
this you wanted to see here.
Yeah. See, so
Yeah.
okay, H is what we expect it to be,
Mm,
and then we need to prove H is equal to something that is of type A1 equals to A2. So like they've already like simplified
yeah.
the type. So that's why the EQ rifle works. Okay, sorry. Jan, what did you want to see?
Well, I mean,
So if I make a parameter here.
yeah, we don't need to write it if it's clear to you as well. But if this EQ of TQ and the other one are abstracted as arguments instead of being something concrete that you can normalize,
Right.
then you know this proof will not no longer work.
If I do one way, TQ of EQ. If I do this way. Oops. Crap. Yeah. Like this. If I do the F here.
Yeah, okay, but that isn't equal, right?
Yes. Wait. Is this? I mean, in Agda, you should be able to prove this, right?
No.
Well, it's
No?
it's still happy.
It's still happy. Okay.
As far as I can tell.
Maybe we can
as far as
prove
I
P
can
equals
tell.
NP today.
Okay, let's do
But this
let's
is
do
very weird. This
Yeah.
can no.
It just pass in the thing I wanted to prove and type rifle, please. I mean, I'll finish my studies here. Like, I don't know.
It's possible that I'm doing something with typing something wrong, or I don't know.
It's all fine.
No.
Yeah.
No, something fishy here.
Yeah.
Uh,
I mean, can you try f of f? I mean, well, that's not gonna type check, of course. Yeah. So.
well, let's this is worth doing. Okay, good.
Yeah. Okay. It's still.
We got an error.
Okay.
You can't type whatever you want, and it doesn't.
Can we see the proof state before
Yes.
rifle again?
So where can I find the thing to? Oh, I can just want to print. But print
like
probably won't give me.
Just 69, like on line 69. If you just have your cursor hover before rifle.
Yeah. Well, this does say that if you give me a1 equals a2, I'll give you an a1 equal. A equals A2.
Yeah.
Oh, maybe that isn't. What's going on here?
Okay, can you add a new line so we can read the whole signature?
Yeah.
Somewhat.
Sure. It's already become.
You can delete all the betas,
Yeah, yeah.
or those three, please.
Am I free to put new lines everywhere, or do I?
Yeah.
Will it give me a complaint? Nothing weird going on, is there?
Oh, that's a check. Maybe you want to print.
Oh, sorry, so print. Yes.
Right.
No.
How is that referred though? I mean, is Lynn doing something smart behind the curtains, or because
With the raffle tactic, yes, but not with the EQ.raffle. Like
Right,
that's
so let's just make it clear.
Yeah, like that's not smart. Like,
okay?
so how
Or if
about
I
this?
switch the arguments around,
Oh yeah, and also can you
can't
construct
That's a very weak way of trying to just outsmart it.
Can you also construct it with GFH instead of just H?
No, GFH, okay.
Yeah.
Has no issue. You can't.
Oh, can we try this in Agda? Because I mean, I would be very,
You
very
want chaos?
surprised if this worked in Agda. Well, but we don't have the EQ type in Agda, or do we? I'm not sure now.
You have the TEQ.
EQ.
Oh yeah.
Yeah, we
Oh, I
have-
see.
yeah.
Oh yeah. You can't go back and forth. Yeah. Oh, how about this? How about this? If we have a fourth example,
Mhm.
Yes.
and we just say H is a prop.
Mhm. Do you want
Or yeah.
to claim that's a counterexample or an example?
Oh no, I don't know. Yeah, and then yeah, so basically take the top one. Yeah, H is prop, and then F is prop to type.
Uh-huh.
And G is type to prop. And then we're going to show,
Mhm.
so colon, and then so EQ, yeah, GFH.
Okay. H. G.
Yeah.
This one surely can't be true.
Okay.
Yeah.
And
I don't know.
what if you reply? Sorry, what if you substitute type by the unit type?
Unit type is called
Unit?
unit.
Yeah.
as type, it doesn't
Type
know.
mismatch.
Also,
GF.
can we just try to prove EQHH?
Yeah.
Okay. Okay.
It must be doing something. I don't. Yeah, I'm confused. So now,
Yeah,
well, I don't know. I'm just going blindly trying things. Because so my guess for the example number 3 or number 2 is that it was using the fact that TQ has a single constructor.
Yeah. But then this should work.
Yeah. Oh, I'm lost.
Okay, so that's pretty interesting, right?
It is, yeah.
Yeah.
Yeah, so how about we make it more take a 5-minute break and then we make it more complicated with
Is there a way of saying this is expected to fail?
I can't
Like
remember, but
counter example. Okay.
that there is.
Okay. We'll figure it out.
Yeah. Yeah, so yeah, let's take a 5-minute break and then I'll show you what happened on the Zulub chat, and because it adds to all of this.
Okay.
Especially this equality thing, they mentioned something, a word that, or 2 words that also sounds nice and intimidating, and yeah. Cool.
Okay.
Okay,
See you
see you
in
in 5.
5.
Yeah, see you in 5. Oh, we're all back.
We're back.
All right. All right. Let me show you what happened on Zulu. So, okay. So I talked about our implementation of TEQ and how we can go back and forth between the two, and how I think this one is illegal. And we got pointed to these notes, which are very good. And explains how like prop is impredicative, and this only works because lean has proof irrelevance. Then prop is an instance of sub-singleton. Okay, so just don't know what that means yet, but just remember this word. Okay, just to give you an overview.
Yeah.
So apparently you are not allowed to go from prop to type, but EQ is a syntactic sub-singleton, so it is allowed to eliminate it to type.
Okay.
Okay. Okay. Then okay, so I think here maybe to start reading here again. So it's not just us that are confused about this. Okay, so this is kind of what's it's pretty encouraging. Like people are asking the questions that I would have wanted to ask, but they just got there ahead of me. So that's pretty cool. Like, don't we still need to boost EQ to TEQ? Otherwise, it will be subject to proof irrelevance, right? This is kind of exactly our question. Because people here were saying that, you know, maybe we can get away with just using EQ and not needing to use TEQ. And then kind of good point here as well, though, our definition of TISO is using the arrow, right?
Yeah.
But that arrow, I think, is prop, is also in prop, right? Yeah, so we should find something else. If we want to stay in type, like we actually need to find something else that we can't just use the arrow. We need to define our own function type. Okay, this stuff. Then so yeah, that's a good question. I'm quite worried about this question. Like, is our version of TEQ proof relevant or not? Like, I don't know. And then I don't know what this word means.
Definitionally equal,
Oh, okay.
perhaps. I don't know.
Yeah, perhaps. Okay, and then we even got David Christensen chiming in, so that if he chimes in, you know, something needs to be explained. So
Yeah.
Okay, so yeah, I'm already struggling with this. So he's asking, like, as I understand it, your question could be rephrased as, are all inhabitants of TQ equal to each other?
Mhm.
Yeah, fair. In lean, they are, because because basically we want to say TEQXY and TEQXY aren't equal to each other. They represent two different parses, right?
Mhm.
Where in prop, we wouldn't care. We would just say, there's something that says X is equal to Y. Why do you care how that happened? Okay.
Yeah.
All right. So that's just thinking out loud for myself. I wasn't trying to explain. Then in lean, they are propositionally equal. This is a bit confusing. They can be proven to be equal. Not it's a prop. So this I don't understand. Oh, this is okay, but the proof here is interesting.
Should consider equal without requiring a proof.
Yeah, so P and Q
Mhm.
are two T, they're each a T saying X equals Y in the proof relevant universe. Like,
Yeah.
shouldn't overload the word universe, but in the proof relevant world. And yeah, if those two proofs were equal, then we would be able to say P equals Q, right? And in this case, we cannot do that with reflexivity. But he did it up here. So, but yeah, like basically, I think this is the thing we want to say is not true. Then we know we have proof relevance, right?
Mhm.
And we also don't want to be able to say this either.
So in these two theorems above,
Mhm.
are we using the fact that there is uniqueness of proof and therefore we can pattern match on it, or is something different? Because we're pattern matching on it, right? By using cases.
Yeah. So this is the thing I wasn't able to do, but yeah, it's clearly possible to pattern match on P, which is TEQ. Yeah.
And this doesn't require K. So I'm a bit confused because we know that Lean doesn't use K, but
Remember, TEQ is in type, not in prop, right?
right.
So in prop, we believe we can't pattern match, and then in type we can. I just wasn't.
Right. So
able
when
to
they
do very-
say Lean doesn't have axiom K, does that only apply to prop, or getting? Yeah, I'm not sure I follow all the way through.
I don't know about axiom K, but I think Lean only has the J elimination rule.
Oh, that's for contradiction.
Yeah,
Ah, right.
it's just for contradiction that it's hard
Yeah.
to like, but it's all possible. Yeah, but this is just about proof relevance versus irrelevance. But it feels connected to K as well, right? Like we saw
In some way.
yeah, like we saw before. It yeah. But yeah, this is pretty interesting. Like you need to pattern match. Might actually be interesting to see this in action. So yeah, here we have x equals y, and we want to prove p equals q, and we do cases on p, which removes it. And yeah, and replaces p with raffle x. And this is probably TEQ raffle, since we've imported it. Oh, where did it go? Yeah, and then we do the same with Q. And these two are exactly the same, so we can just yeah, so we should be able to say match. Well, okay. Wait, it's usually case raffle, yeah. Raffle X. Sorry, can we do this? Yeah, see, that's always like too many variable names. Okay. Oh, okay. Okay. That's so weird, right? So usually I would have access to the variable that I pass to the constructor.
Yes.
And
But
this,
it's implicit, is it? So you need to
oh, one of them isn't implicit.
let's see. Yes, you're right.
Right?
That's odd.
It really
So it doesn't bind it? Doesn't bind that. Weird.
but maybe no, it is right here.
Yes.
Right? That freaks me out. But like
I don't
okay,
get that.
yeah.
Maybe you can get hold of it on P. You say P dot P. No.
Wait a second.
Or EQ dot referl. You have to use the full name.
Yeah, see here, right? This is how
Yes.
net is defined, and there we would be able to. And then
If you write TEQ dot referl instead, does it? Is that how?
no, it doesn't allow you.
Doesn't allow you to pattern
yeah,
match.
I think now
Okay.
you go match P with
Yeah.
Raffle, and then by, sorry.
Then you need the binder.
In here.
Yeah. So now you have to put the parameter. Huh?
Raffle doesn't take parameters, right?
It does.
Doesn't it? Does it? Oh, okay.
Yeah. It takes one.
Okay, okay.
Okay. Too many arguments. Okay. Not. I mean. Oh, I can
So
only.
you have X and Y and P and Q, is that?
Yeah.
Oh, yeah.
Yeah.
Ah, I see. Sorry, yeah.
Yeah. Yeah, you can't. Okay, I see now. You can't like. You're destructing it, right? Saying
Yeah.
X equals Y. And but you can only provide one parameter. So you can't provide X and Y here. So and you can't provide a parameter that doesn't exist. That's why it's hard to do it when you do it up here. So actually, print. This might help.
Case is on.
Yeah. But then,
Blah blah blah.
yeah, you need HEQ there. So it's fun. Hmm. Yeah. Okay. Cool. I got nothing.
No.
Yeah. But yeah, we are pattern matching on P. It is just weird. And Q, and then it gives us rifle X where somehow Y has been eliminated. And then yeah, it is just reflexivity now. Okay. I don't know how interesting that was, but I think this also works, which we don't want. Okay, so here, the fact that these are true, right? That we don't
Yes.
want to be in lean is actually an instance of a deep issue in type theory. So yay, we found a bug. Everyone used to just assume that this was the case, but nobody succeeded in proving it. Some version of it was, well, what did they assume was the case? That this was an issue, and they didn't succeed to prove that it was an issue. I'm gonna assume that. Some version of it, yeah, no, you
So
read it.
I understand that they assumed it was true, but they didn't succeed in proving it was true.
So it was an issue, or this is
Well,
true?
it had. So I understand that it has the common issue because everyone assumed it was true, but it was never proved.
Hmm. So no one has proven this. That feels weird. Because he did it in 3 lines, so I'm kind of
Yeah, there's some other meaning here. Isn't it the case that I think, isn't this the case for homotopy type theory, which is that everyone assumed that there was only one proof of x equals x, but no one. So a lot of systems were built with that assumption, but then it turns out not to be true because you can define systems which there are many proofs of x equals, many non-equivalent proofs of x equals x.
Yeah, I think you're onto something. So like, because here it says like some version of it was often adopted as an axiom. The things to search for are UIP, so we just covered that.
Yes.
And axiom K, which we just talked about. So, and yeah, it was provable using Coquan's initial formulation of dependent pattern matching, but the proof never went through. Then Hoffman and Streicher published the groupoid interpretation of type theory, in which they give a model in which this axiom is false.
Yeah.
In Lean, we just treat types as sets, so it's fine. Okay. And you don't really have to worry about which equality proof you have. But this is not true in every system out there, and it rules out certain type system features that are incompatible with it.
Okay.
So it's a lot to take.
Presumably makes difficult to do this homotopy type theory in Lean then.
Yeah. I think in these notes, I also mentioned this. Yeah, so here with proof irrelevance, homotopy type theory and other constructive or intuitionistic type theories built on data inequality proofs are therefore incompatible with proof irrelevance. So
what does this mean for us?
Yeah.
Oh, there was a section. There was a section on large elimination. Have you looked at that?
I have not. I've seen it. But I saw it exists, but I did not read it.
Well, we can defer it.
Well, it okay, so this, yeah, maybe this is interesting.
Although it's probably interesting to note that this looks like it's from 2018, and so maybe
so
from Lean 3 or Lean 2.
Oh, definitely.
But who knows? I don't know if they have different type theories. So
yeah, probably not.
Probably not.
Yeah.
Because they link to this from the Zulip.
Yes.
Okay, so it's probably still relevant then.
Yeah, hopefully. Yeah, hopefully. And there's small elimination here as well. So but okay, let's go back to the Zulu, like, because there's more.
There's more. Oh my gosh.
Yeah, just a little more.
Yeah.
Okay.
So sub-singleton just means that it has 1 or 0 inhabitants. Is that right? So singleton would mean it has exactly one inhabitant, and sub-singleton means it can have 0 or 1
Ooh, I like
inhabitants.
that.
Is that true?
That would
Don't
be.
know.
I
It
hope
would be
that's
nice, wouldn't it? At
Uh,
most one element. As even NLab agrees.
Oh, there. Did you get it?
I just read it in the. A sub-singleton is generally refers to a subset having at most one element.
Okay, great. Okay.
So maybe that is.
Okay. Or we could have rate this. Okay, so that's the 1. Okay. Okay, so wait, everything in code is actually a sub-singleton. Like if you talk about Java singletons, they're actually all sub-singletons because they might not have been initiated.
Hmm.
Right. Okay.
Well, but if you think of it as a type, they still have an element at least, right?
Ah,
So I mean,
yeah.
Yeah, like the type theory is independent of instantiation in the code or not.
Yeah. Yeah. Yeah, you're right. Okay, so I'm a bit surprised. Okay, so this saying. So I feel this makes this construction useless in Lean. It's talking about TEQ, right?
Oh no. This is the pillar of our project.
Well, I would be happy. But I still want proof relevance somehow. Right? But it would be nice to be able to use EQ and use I think there's some way to use EQ and to still have the regex is from string to type and not from string to prop. But then have everything you want to prove in terms of equality still be in prop. So the parses are in type, but the proofs of equality are in prop. I think there's but so that's another question I have. Yeah, did we need to go all out on type, right? Or did we actually just need string to type and nothing else? So
yeah, it's a good point.
yeah, I don't know. I think yeah. All I can say now, I think it is a question worth asking. Okay, but okay, so I was surprised. However, as I thought, systems without what is UIP again? It's just for reference.
Uniqueness of proof.
Yeah.
Uniqueness of
identity proof. Yeah.
Okay.
Yes.
Cool. And /k. So our k is back. Basically define equality the same way, but without having proof irrelevance in the kernel. It no longer even becomes provable propositionally that all instances of the identity type are equal. Why does this fail with TEQ here? Okay. UIP is known. We knew this. No. Some people know. Okay. Did not say for all, but there exist people that know that UIP is infectious like this. Otherwise, we could do homotopy type theory by just moving to TEQ, which I think that's.
Is that true?
Yeah, I think that's to go back to this statement, it seems that this proof irrelevance disqualifies Lean from being something for homotopy type theory. So if there was a way to get proof relevance back, then you could just move to that. So if we're like, okay, we want proof irrelevance, so we want to use TEQ, then we could just do that. But UIP is infectious. That's kind of sad. So, okay, so the lean 3 homotopy type theory repo, so this was attempted, does define type valued equality. This looks very familiar. That's a bit weird, but otherwise, like there's not two A's here, but just one. And implement a rewrite tactic, which, by the way, it's very hard to do rewrite on TEQ. So, like, as, I've not been able to do, but someone has in lean 3, which is pretty impressive. Yeah, so it used to be possible, at least. I believe it should be possible again, but not fun, not fun. But it also disables large elimination altogether. Okay, so that's the large elimination that we should read about. And yeah, this doesn't exist in the lean 4 repo, so we're on our own-ish. Although these people have been very helpful. Okay, but oh, maybe not. Someone had a similar idea here. Okay, so right there, to do homotopy type theory, you need to disable large elimination from prop. They don't modify the kernel, they just check separately that large elimination isn't used. Okay. Interesting. Okay, I wonder if we define the identity type to lie in type instead of prop, maybe that isn't enough to avoid inconsistency with univalence, but what about just don't use prop at all and make type effectively the lowest universe? Okay, that's kind of what we were trying to do.
Yeah.
Okay. So we don't have large elimination, basically prop is useless. That's interesting.
Well, I need to go now.
Okay.
Yeah.
I'll catch you in the next one. It was very interesting
Thanks,
today.
Jan.
Yeah,
Yeah, thank
thanks
you.
for coming. Very helpful.
Bye.
Bye.
Okay, just a little more.
Yeah.
Yeah.
I was just worried. It says at least the proof of false won't work.
Oh.
That's we that should be the very least, right? We don't want a proof of false. I do have a feeling we've strayed somewhat because, like,
okay.
No. What I mean is, this is interesting, but
yeah,
I don't think in Connell's repo he needs like homotopy type theory to do what he's doing. So, like, when we start talking about univalence and so on, I think this is too advanced. It's like we must be missing something.
Well,
No, you can have proof relevance without having to do homotopy type theory.
no, you
Is
can't.
my hope. Is my hope.
Yeah. But you can't do homotopy type theory without having
Yes.
relevance.
Yes.
So that's why it's connected. Like we don't
Yeah.
need
Yeah.
homotopy type theory, but we need to learn from some of their struggles.
Yeah. I see.
That's all that's going on here. So it's so what I'm gathering is they were also trying to do exactly what we're doing.
Yep.
Well, they were going further. Like so not just redefining equal from prop to type, but also trying to disable large elimination. And apparently that might be enough to get proof relevance, but it doesn't look very possible. If we go back here, I just want to check if it is some idea, but you realized it doesn't work. Inconsistent with univalence and large elimination. So I think the conclusion question here, what I want to write. Okay, wait, I want one more question, just one more piece of data before I
Yeah.
reply here. But so this is the last thing I wanted to get at. Is I think this was important to us, that we go from a list to a type,
Yes.
a list to a prop. Although, okay, maybe the question is like what is a parse? So for this, we aren't capturing anything. We're just returning true and false, right? Does it parse or does it not? And
Yes.
how did we get there, right? So in our true and false, in this case, in coq was prop.
Yes.
In this case, it's a type. So in this prop, we would not know how it was parsed.
Exactly, but we would know it passes or not. Yes.
Would know, or theoretically would know. We think we would know.
Yeah, this is my model, is like, well, yeah, you're basically constructing the type one, you're constructing something that passes rather than just telling you whether it passes or not. That type, the thing in type could be compiled into a parser, something which passes, where the prop one couldn't be. Like it doesn't. You can't make a program out of it that does any work.
Yeah. Okay. So then, for example, these proofs, right?
Yes.
Could all, yeah. Oh, this is actually, I modified this, I guess. Yeah, but these could be, instead of being the TEQ, which is triple equal is, this could just be EQ. Right? All of this. This is actually fine, because this was already in prop. I think. Just double check that. Well, yeah,
Right.
we'll just do this. Like, okay, and apparently something like this.
Ooh.
All right.
That's interesting. I've never seen an error from the kernel before.
Oh, yeah. Yeah, make sure to get that one on video. Yeah. All right. Interesting. But I think there is a equiv or something
Yeah, they were
maybe.
saying there was an equiv, capital E equiv.
Yeah, so we could probably look into that. But yeah, we might not need TEQ.
No, because when you think about it, yes, when you think about it in terms of prop versus type, like the computational content of the REFL here is that it gives you the X, the X that makes the equality. So you pass an X in, you get an X equals X. Well, it's holding the X that is it's not just telling you whether it's equal or not. It still contains the X there. But that's also true for the normal equality. So what extra information is available for TEQ that's not available for prop in the prop version? Because
Yeah,
we've already seen you can pattern match on both of them, so you can get the X out of both of them.
no.
You can't? Oh, right. With the one that David Christensen.
We can do, okay. Let's we can do. Okay, yeah, you're right.
So what does the TEQ hold that the prop one doesn't? Doesn't seem to be anything.
No.
But I think like you said, the motivation was for the parser to be in type.
Yeah.
Maybe that's why we needed this TEQ, was because this is going to be like a component of the parser.
Yeah.
Don't know.
Yeah, I think that's my guess here. And I think there's still a question for me. Is everything proof irrelevant? Like,
Yeah.
like do I get proof relevance for this type, right?
Yes.
Because otherwise, like, we could just be in prop, like.
Yeah, exactly. So I think if we're only interested in EQ, then there doesn't seem to be a difference. Because like in that thing, we just prove that they're all the same. You can they're propositionally all equal.
Yeah.
But this is what we really care about. Are these all equal?
Yeah.
Do we have different parsers? Can we tell them apart in the the type level or whatever, or the
Yeah, so I think
the TEQ is a means to an end, because we're going to need equality types when defining this thing, and so it's just a matter of like, well, you need those TEQ types because you're going to be expressing everything in type. It's not we don't need proof relevance for equality. We need proof relevance for this. But it's like a means to an end. You need the TEQ because everything needs to be in type.
Well, I don't know.
Maybe.
So I think here, this is interesting, right?
Yes.
And here, right? But and even here. Okay, so this here's maybe the best one. Yeah. Here you need TEQ, right? And here. Because otherwise you're returning something in prop.
Yes. I see your point, because like if you just ignore the fun part and just the right hand side, so how many? If we just care like on line 44, W triple equals empty. list.
Yeah.
We don't really need more than one proof of equality. Really, we only care that
Yeah.
we're happy with one way that they're equal. But
Yes.
the function type, we want there to be multiple ways for the function type to be inhabited.
Well, actually, like if you just go down to or, right?
Uh-huh.
Like this will return a type
Yes.
U, and this will return a type, and then you're putting them inside a sum type, an either, right? And this represents your parse, right?
So you want to know which one had been used. It's not enough to know that at least well, one or the other was matched. You want to know exactly which one it was.
Well, as I say that or think that, I was thinking I'm like, am I now just storing all parsable parses? But yeah, I'm still getting out the actual parse. Yeah, so here TEQ is like quite important. It is.
Yeah.
It is part of our parse. Ah, so close. I was like, we just don't need it. And then so Connell asked a question that kind of follows up from this. It's if you don't use type or prop, like how would you represent the parse? And so I think at this level, right, is gonna cool. Yeah, I'll put it in a sum type. I'll put it in a product type. Yeah, easy stuff. But if we think at this case, it would be like if W equals A, the list of just A, then return an A. And if it doesn't, then like then fail, right?
Yes.
And then at this level where you do the product, go like, well, this side failed, so we don't have to construct that. Like that's not part of the parse. It is the left side. So maybe what would be good is to print out some parses and look at them. Yeah. But I don't know what to reply to the Zulup and
No.
it's like yeah, I think I can do well. The naive reply is okay. We understood. I wouldn't say we understood everything.
No. Wait.
More reading to do.
Yes.
But it seems like there might not be a way to prove relevance in lean. The use case is that we want to represent a language using maybe and we want prove relevance to what is the word? It's not
We want to distinguish between different
distinguish. I feel like yeah, okay.
yes.
Just type letters, it'll be
You'll figure it out.
yeah. Yeah. That's unfortunately that's still the best reply I can do. Like
Yeah. We need to think about it more. The worst that can happen is they just say, we don't know what you mean. In which case we said, well, we don't know what we mean either.
yeah.
So we're not lost anything.
Yeah. But it's yeah. It's pretty interesting how comfortable some people are talking about this and how also we aren't the only ones that are struggling with it and how also we aren't the only ones that want this. Yeah, but it seems pretty hard to understand, but like it doesn't seem like there's a lot to understand. It's just very complicated. A very small amount of information that's very hard to understand. But not a lot of information. Does that make sense? It's almost like, oh, monad, like it's a small amount of information, but it's really hard to understand. This seems like it would be, or maybe, yeah.
Yes. Do you remember in Coq there was something called S prop as well, which was like a new feature that added to prop, which was proof. I think that adds another thing to the mix, because that was like proof irrelevant prop. So
was prop not proof irrelevant?
well, given that there's a separate type called sprop, which is for proof irrelevant prop, then maybe not. Or maybe there are different degrees of irrelevance.
No, it's interesting because the notes also mentioned that in Coq you have proof relevance, like in Agda.
Mm-hmm.
Well, which
was somehow different.
There, yeah.
But we never used sprop because I think it was a newish feature, and it wasn't clear that we needed it.
Yeah. Well, that was very interesting. I'm going to stop the stream.
Yes.
Yeah.
Thank you, everybody. I wasn't looking at the chat, so
yeah, there was.
I just remembered now to look at the chat.
Maybe one person watching. So that's kind of the average. So yeah. Cool. Cool. Have a good day.